An example problem. This is a solid staying a solid. Example here. We have stainless steel, little 12 millimeter ball bearings leaving a furnace. I happen to have one laying around here. It's about a half inch, give or take. Little ball of stainless steel. It's a nice representation of what that looks like. Not a lot of mass. Right? That's just a standard size A 8.5 by 11 paper you can see that's rolling around on. So not a lot of mass, very small amount of mass. About 12 millimeters, about a half inch. And if I can find somewhere on my desk to corral that, I'm going to set it down. Okay. It's going to come out of a furnace. So it's probably going through some sort of a heat treatment after it's been generated. And so that way it doesn't shatter once we load it up with some sort of a load. It's a very common thing we'll do there. Now I'm looking in my notes. Well, here we go. So in the notes, in my notes here, they've given me this particular problem that I pulled. They've given me that the uh, density for this stainless steel is about 8,085 kilograms per cubic meter. And the specific heat for this stainless steel is about 0.48 kilojoules per kilogram Kelvin. Now, if they didn't give that to me, you do have in your textbook table A3. Table A3 is common properties for liquids, solids, and some foods. And notice you've got down here a value for steel mild. That's not stainless steel. We have to add some additional metals to stainless steel to make it a non-corrosive alloy where it resists corrosion. But you can see these values here. About 8,000 is my density and about zero point 0.5 is my specific heat. We're pretty close to that. Stainless steel is, again, kind of an alloy of steel, so we should expect similar properties. All that to say, this would get you in the ballpark if we were to use these values. But the values that this particular textbook has provided is what we're going to use. Those are the more realistic values we'll use. So if we record our givens here for this particular problem, so they've given us a diameter for this stainless steel ball of 12 millimeters. They've given us a initial temperature of 900 degrees C. They've given us a final temperature of 800 degrees C, so a 100-degree drop in temperature. They've given us a density of 8,085 kilograms per meters cubed, and they've given us a specific heat for the stainless steel of 0.48. That'll be kilojoules per kilogram Kelvin, energy per mass per temperature. And what we want to know is how much heat is transferred to the air. So we want to I'm just going to say find. That's easier to write. Find the heat transfer. Okay. And here's where we say, all right, what's good? Rule, law, equation, relationship for finding heat transfer. What tools do we have? We've organized, we know what we're looking for. We know what we know. How do we find what we're looking for? Well, it's an unknown energy quantity. First law is a really good place to start. How do I write a first law equation? I draw my system. There it is. That's it. Just a little circle. What's crossing the boundary? Well, heat. And it's cooling, so that's heat out. If I'm worried about the heat out, I'm probably not worried about any heat in. I don't see any work being done to it. It's probably on a conveyor belt, so it's probably going, there's probably some work, a small amount of work being done to move it along a conveyor belt, but that's not really enough to worry about. It's probably moving at a constant speed, so there's no change in kinetic energy, and they've not said anything about potential energy. The main thing, the main energy going on here is going to be this heat transfer. So I can write my first law just simply from that. Again, add your in, subtract your outs. That means minus Q out is going to equal the change in the energy for the system. Well, assuming that it's moving at the same speed along as it comes out of the oven and moving at a relatively constant elevation, the only energy changing the right-hand side is going to be delta U. I guess I could switch to full-blown camera now. All right, so again, looking for Q, draw my system, draw all the energies crossing the boundary. That's going to be, and then add the in, subtract the out. So it's minus Q out is going to equal the change in the energy of the system. That's just going to be M delta U. First law, done. Now, okay, well, what do I know here? I'm looking for Q, so I need to know these other things. All right, well, how can we find the mass? And this one's a little outside the ordinary for us, but normally somebody will say, well, we know the density. If I could use the volume, right? The mass is equal to density times volume. Say, okay, well, how do we find the volume? Can we find the volume? And somebody will say, yeah, it's just a sphere. Yes, okay. And then hopefully somebody will remember the formula for volume of a sphere, 4/3 pi r cubed, if memory serves. In fact, I'm literally going to pause this video and go look that up and make sure I'm not telling you wrong because I don't know it off the top of my head. It's not the kind of thing I memorize. Okay, yeah, I started doubting myself. It is, in fact, 4/3 pi r cubed is the volume of a sphere. So, and I know the diameter, twice uh, twice the radius, so we can find that. So mass is a findable quantity. What about the U values? Well, we just got done in the previous videos talking about if I've got a solid staying a solid or liquid staying a liquid, then I can use C sub P, at least in this text, they use C sub P times the change in temperature to quantify delta U. Again, if it's an ideal gas, we're going to use C sub V, but in your text for a solid or a liquid, they'll use C sub P. Many texts, they'll just use C. They won't differentiate because there's no difference between C sub P and C sub V for solids and liquids. I'm going to go ahead and distribute my negative sign here. So this becomes Q out equals M C sub P T1 minus T2. I took the negative sign here, threw it in there. And so yeah, now I just need to find these other quantities. I know C sub P, that's known. I know my temperatures, so I just need to do some calculations. So let's find the mass. The mass is going to be the density, 85 kilograms per meters cubed, times the volume. Volume is going to be 4/3 of pi, and also 4/3 pi of the radius cubed. Well, I've got diameter, and diameter is in 12 millimeters. So I'm going to write in here, this is 0.012 meters. I need half of that, and that's going to get cubed. All right, to keep this video from getting too long, I'm going to pause and run those numbers. You do the same. Go ahead and pause here and figure out what this number is. All right, I've got here a value of 0.00732. And the units there, if you look at them, the meters cubed are going to go away. I should be left with kilograms. That's really small. Well, yeah, remember, that's it, right? So yeah, it's going to be pretty small. I don't know if that's 7 grams off the top of my head or not, but it's probably, that's not unrealistic. Okay, now on to Q out. Q out is going to equal this mass, which we now know, 0.00732 kilograms, times specific heat, 0.48 kilojoules per kilogram Kelvin, times then our change in temperature, which Again, I've thrown a negative sign in here, so now it's going to be um, 900 minus 800. A change in Celsius is a change in Kelvin. So the units are just going to leave me with kilojoules. Go ahead and run this one out since I've got everything queued up here. So that's my mass times 0.48. It's my specific heat times 100 is my energy change, and this ends up being 0.351 kilojoules is what I have. So not a lot of energy, but that's actually a good amount considering, again, it's just this little guy is all I've got there. And so yeah. Oh, yeah, I looked up volume of a cylinder just on Google earlier. Okay, here we go. All right. And then a lot of times I'll go ahead and throw this one out there. Kind of transitions us into flowing mass type problems. So, okay, well, you know what? If you've got, let's say, 1,000 of those every minute, let's say I'm running 1,000 of those every minute, how much, at what rate is the atmosphere absorbing heat? All right. So, what have I got? I've got a stream of these little balls coming out of some oven, and every one of those is losing some amount of heat to the atmosphere. What you found is you found how much heat is being lost per ball. If I've got 1,000 of those going into the and every one of those is going into the atmosphere. And so we're rolling m dot is basically 1,000 balls per minute. What does that look like? All right, well, again, each one of these guys is losing heat from the ball into the atmosphere. So basically, the rate at which heat is going out of the balls is equal to the rate at which heat is going into the atmosphere. Right? So I know how much, I know up here how much energy we're losing per ball, and I know how many balls per minute we're running. So I can just simply do this. I can say, well, you know what? The Q in, the rate, Q dot in, the rate at which the atmosphere is absorbing heat out of this product stream is going to be 1,000 of these. Trying to write that in cursive when I shouldn't. 1,000 of these balls every minute. Let's go ahead and get rid of the minutes here so we can go to watts. Watts are joules per second. So if I get rid of the minutes here, that's 1 minute for every 60 seconds. So that'll tell me how many balls per second we're running, and then I multiply that by the value we just found up above, 0.351 kilojoule for every ball. We can run those numbers pretty quickly here. 0.351 divided by 60, and then times 1,000. So we're going to run about 5.85 kilowatts because it's going to be kilojoules per second, or kilowatts. All right, Steve, what the heck are we trying to do here? How does that help us? This helps us that if I've got some sort of a factory running these balls out, this product stream coming out, and I need to know how much air conditioning, how big of an air conditioning system do I need in order to maintain a safe temperature for my workers in the factory? Well, this is what we would be looking at. I could use this to figure out how many tons of cooling, how many BTUs divided by a certain amount of time, or however you want to size your air conditioning unit. This gives you an idea what that looks like. All right, that's a nice enough place to stop this video. And we'll pick up one more lecture video or one more theory lecture part, and then we'll call it good for lecture 10.